All right, let's jump right into something that sounds kind of impossible. Imagine a fighter jet, this incredible piece of machinery, just blasting through the sky at over 1,000 kilometers an hour. It's surrounded by air, right? But here's the crazy part. That very same air isn't cooling it down. It's actively trying to cook it. So how on earth do you air condition something that's being superheated by the very atmosphere it's flying through? And this isn't about keeping the pilot comfortable. Not really. This is a life or death engineering problem. The friction from moving that fast can make the jet's skin absolutely scorching hot. Without some kind of insanely powerful cooling system, all those sensitive electronics would just fry. And the pilot? Well, they wouldn't stand a chance. The solution is just as brilliant as it is counterintuitive. They basically fight fire with fire, or in this case, they fight hot air with, you guessed it, hot air. So to really get how the solution works, we first have to wrap our heads around the sheer scale of the problem. We are talking about some seriously extreme physics here, where the normal rules just don't apply. At these speeds, and yeah, that number comes straight from a real-world engineering example for a fighter plane, the air molecules just can't get out of the way fast enough. They end up slamming into the aircraft and piling up. It's a process called ram compression, and that compression, plus all that friction, generates a ton of heat. So the faster you go, the hotter everything around you gets, which makes any kind of standard air conditioner pretty much useless. Okay, so if the outside air is the problem, how in the world can it also be the solution? Well, this is where we get to the beautiful core principle, a little trick of thermodynamics that makes this whole thing possible. You've definitely experienced this yourself. Ever used one of those manual bike pumps and felt the pump itself get really warm? That's the heat of compression. And on the flip side, have you ever used a can of compressed air to clean your keyboard and felt the can get shockingly cold? That is the cold from rapid expansion. Squeeze air, it gets hot. Let it expand really fast, it gets cold. This simple, everyday principle is the engine behind our jet's entire cooling system. All right, so with that key idea in our back pocket, let's follow a single packet of air on its incredible journey. We're going to start with a basic setup, what engineers call a simple air refrigeration system, just to see this principle in action. So let's follow the air. First, it gets slammed into the engine intake, getting compressed and hot just because the jet is moving so fast. Then, an engine compressor squeezes it even more, making it incredibly hot. Now, this super hot, high-pressure air gets sent through a heat exchanger. Think of it like a radiator, which vents some of that heat away. But the air is still under a ton of pressure. And here comes the magic trick. This now cooler, high-pressure air is blasted through a turbine, which lets it expand almost instantly. And just like that spray can, its temperature absolutely plummets, creating a stream of freezing cold air for the pilot and all the vital equipment. Now, that simple cycle is pretty clever. But for a fighter jet that's pushing the limits of performance, it's just not quite enough. To get the kind of extreme cooling they really need, engineers had to give the system a major power up. And they came up with something called the bootstrap system. It's a cool name, right? It comes from that old saying, pulling yourself up by your own bootstraps, because the system actually uses its own parts to power a second stage of cooling. It basically feeds itself to become even more powerful and make the final air output even colder. So how's it work? Well, the bootstrap system basically adds a whole second stage to the process. After the air gets cooled down the first time, instead of expanding it right away, it gets sent to a second compressor. And this second compressor is powered by the cooling turbine itself. This squeezes the air even more, which then goes through a second heat exchanger. So with this extra step of compressing and cooling, when the air finally expands, the temperature drop is way, way more dramatic. So why go through all this trouble? I mean, why not just use a fancy version of the air conditioner you've got in your car? Well, in aerospace engineering, every single choice is a trade-off, and using plain old air as your refrigerant has some very specific pros and cons. On the plus side, air is free, it's everywhere, and you're never going to run out mid-flight. And this is huge, it's not flammable or toxic, which is a massive win for safety. The whole system is also pretty lightweight compared to other options. But then there are the downsides. It is not efficient at all. It needs huge amounts of air, and you've got to worry about any moisture in that air freezing up the lines and causing a blockage. But here's the bottom line. For a fighter jet, safety and low weight trump almost everything else. Let's put a hard number on that low efficiency claim. The source material actually gives us a detailed calculation for the very same bootstrap system we've been talking about as it's used on a fighter jet. And the result is a coefficient of performance, or COP, of just 0.1. Now, to put that in perspective, the AC unit in your house probably has a COP of somewhere between 2 and 4. This means that for every single unit of cooling the jet system creates, it eats up 10 units of energy from the engine to do it. It is incredibly power hungry. But it gets the job done safely using a refrigerant that weighs nothing and can't catch on fire.
And that just leaves us with a really fascinating thought. By one very important measure, this system is terribly inefficient. But it's also tough, it's safe, and it's perfectly built for one of the most demanding environments you can possibly imagine. It's a great reminder that in the world of high-stakes engineering, the most elegant solution isn't always the one with the best numbers, but the one that best answers the mail for a unique and extreme mission.